and Dali Wireless today. Looking at the registration list, this is going to be a pretty worldwide webinar with far above 100 participants from America, all of Europe, Africa, Middle East, including Malaysia, Singapore and Hong Kong, where it's now already past midnight. So thanks all for joining, whatever day and night time it may be at your location. Today's topic will be an introduction to radio access network virtualization, how it works, and why this is relevant to operators and users. We are very happy to have two high-profile speakers here on this session. The first one will be Nick Marshall, Research Director at ABI Research, who is closely monitoring the market trends for indoor solutions and capacity situations. The second speaker will be Wolfgang Weber, Vice President of Business Development at Dali Wireless and former CTO of Swisscom, the #1 operator in Switzerland, with a rich experience in mobile networks, both from a technical and a business perspective. My name is Markus Ulietz. I do business development at Dali Wireless for Europe, Middle East and Africa, and I'll be your moderator today. So during the session, please feel free to type in any questions that you may have in the chat panel at any time. We will collect them and answer them at the Q&A session towards the end of the session. Also, a playback version of this webinar will be available on the Dali Wireless webpage, and we will send you the link shortly after the session in a follow-up email. So with that, now let me pass the microphone over to Nick for the first talk. Go ahead, please.
Okay, thank you, Marcus, for that introduction, and welcome to everybody who dialed in to listen today. It's a pleasure to be part of this webinar with Wolfgang and Marcus from Dali Wireless. A couple of words on the format today is that I'll kick off with an outline of the major trends and challenges we see driving the in-building and in-venue wireless market, and take a look at the market potential. I'll follow this with a discussion on how the RAN is evolving to meet these challenges by looking at how RAN virtualization is enabled by building on a CRAN foundation. And then before handing over to Wolfgang and Marcus for a deep dive discussion on Dali's implementation of RAN virtualization, I'll describe some of the benefits we see coming from this architecture. And as Marcus mentioned, there'll be some time at the end for Q&A. So we hope you enjoyed today's webinar. First, just a few words about ABI for those who may not be familiar with us. We've been in business for 25 years. We're a technology market intelligence company operating across 11 research sectors, as you can see there. We try to provide our customers with insight and how technology is adopted into vertical markets. And I won't dwell on this slide, but it's in the package for reference. So with that, on to our webinar. This is the agenda. I'll talk about the drivers in the in-building and in-venue wireless market, including the growth in mobile traffic and some of its characteristics. We'll outline the market potential for in-building and venue wireless before moving on to describe RAN evolution. Then we define RAN virtualization and outline its benefits before passing over to Wolfgang, who will look at how Dali Wireless has implemented RAN virtualization. Exponentially growing traffic is the #1 challenge for many mobile network operators worldwide. And as we see here, we predict a 35 times growth in 4G traffic by 2019. And actually, for the first time this year, 4G mobile traffic will exceed all other traffic, which is a bit of a milestone. Subscriber usage patterns are also changing. There's an effect we call the 4G multiplier effect. The faster the data rate the subscribers have, the more they use it, and the more apps take advantage of it, and data traffic growth is compounded or multiplied. Another characteristic is video is the fastest growing and dominant traffic type. We estimate that video will grow by 17 times between 2013 and 2019. Video, of course, requires low jitter and high bandwidth in access in comparison to other traffic types. Also, between 80 and 95% of all mobile traffic is generated or consumed indoors, and deep in-building and venue 5-bar coverage is expected by all subscribers today. Traffic, there are some characteristics of traffic that make in-building wireless system design interesting. Traffic is tidal. It is lower in an enterprise, for instance, outside of working hours and high during working hours. An indoor venue wireless system must be flexible enough to cater for this tidal ebb and flow of traffic. So we can think of using various architectures for RF distribution in buildings such as DAS and small cells, which are also good choices. However, a conventional DAS does not scale down economically, and small cells do not scale up economically. An alternative approach is what's required. But first, let's look at the market potential for in-building and in-venue wireless distribution systems. And I've tried to draw this here by showing that the blended average penetration for all commercial buildings worldwide is about 2%. Therefore, there's a great potential for RF distribution. I've also tried to show here that DAS architectures are popular in the very large building areas and find less popularity in the medium and small categories. Conversely, small cells are ideally suited to the small and medium-sized buildings and must be carefully engineered to scale up to larger building areas. There are many solutions on the market, and as we shall see from Dali Wireless today, state-of-the-art DAS systems cost-effectively scale down to smaller building sizes and compete with small cells. So let's look at the market potential for in-building and venue wireless distribution equipment. And so we can quite simply combine the equipment market for active and passive DAS systems and repeaters, enterprise femtocells or small cells, metro cells, and enterprise Wi-Fi equipment. And so based on this compilation, we can see that between 2014 and 2019, the equipment market grows by 3 times to reach, in our estimation, a value of more than 25 billion by 2019 worldwide. Taking the same data, we can see there are regional differences, and you can see that although North America was the largest market in 2014, it is the Asia-Pacific region growing by 4 times, which becomes the largest market in 2019. Other regions grow by between 2 and 3 times in the same time frame. In 2019, the market in Asia-Pacific will exceed that of North America by a third, according to our estimates. As we shall see later on in the webinar, the in-building and venue wireless market will be among the first to benefit from virtualization. So switching gears and digging a little deeper into the architecture that's required for RF distribution, we start to see a trend which can be leveraged towards meeting the challenges of RF distribution. Recall the challenges we mentioned early on in one of the slides. These are managing the relentless growth in traffic thanks to the 4G multiplier effect, providing low jitter and high bandwidth for video, providing 5-bar coverage indoors where the traffic is, and managing the tidal ebb and flow of traffic. And we must do all this while lowering TCO to render systems attractive at smaller building sizes and enlarge the available market. So as shown in this slide, the conventional RAN with this co-located baseband and radio unit has evolved to first a distributed RAN with remote radio heads connected by CPRI, usually over fiber fronthaul, back to a baseband. The next step involves centralizing or pooling multiple basebands in one location, sometimes called a baseband hotel, and again using CPRI over fiber to connect the remote radio heads. This is called CRAN. The virtualization step is next and builds on the CRAN foundation by packetizing the CPRI data and providing a destination address so that, just like in packet switching, any RF source can be routed to any antenna. So I'll try and draw this out in a bit more detail. Apologies for the artwork. So in this diagram here, the conventional RAN, the radio base station contains a baseband for digital processing of the protocol and a radio unit for transmission and reception of radio signals connected to antenna by coaxial cable. When we switch to using fiber, we can move the radio head closer to the antenna to help save on RF losses, since shorter coaxial cable runs are required. The connection between the baseband and the remote radio header front haul must be high-speed, low-latency transport, such as fiber, where typical data rates can reach as high as 10 gigabits per second. Moving to the next step, centralized RAN, which now becomes compatible with conventional or active DAS, since it uses fiber to distribute a signal to the radio heads throughout the building. By locating the baseband in a central location, many remote radio heads can be supported from a common baseband scheduler in a controlled environment. The last step is to virtualize the RAN, much like in virtual computing, where a virtual machine has access to all the CPU resources thanks to a hypervisor. In the virtual RAN, access to the baseband and radio resources is managed by an RF router, the equivalent of a hypervisor. It is the RF router which assigns these resources to the user terminals camping in the coverage areas. Now we have a true many-to-many RF routed distribution framework, which, as we shall see from Dali, is protocol, vendor, and MNO agnostic. And since the routing is packet switched and not circuit switched, it saves on in-building fiber infrastructure. Also, since our system is now fully digital, we can take advantage of that and provide exact capacity matched according to demand, and even do that autonomously via a network management system. So before I hand over to Wolfgang to dig a little deeper, I just wanted to mention a few of the advantages we see from RAN virtualization. Since the signals are routed and not switched, we have a trunking gain, since we avoid physically connecting every source to every antenna. Benefiting from digital network management, we can match capacity to demand exactly. Over provisioning is history. We have a true multi-point to multi-point operation, which is technology, MNO, and even vendor agnostic. We can do away with the point of interface of DAS tray, which consumes a lot of energy. Since we are using low latency pooled scheduling in the system, we can improve the quality of the experience for the subscriber and easily implement advanced techniques required by the progression of 3GPP. The overall result is that systems of this type minimize the per bit delivered costs for the subscriber and system operator, one of the goals we had mentioned. So to finish off, we can say that the trends we are seeing, traffic is dynamic, is growing exponentially, and is unrelenting. Systems have to handle this. Subscribers must expect to be always connected everywhere is the new norm. Indoor service is becoming more important than outdoor. That's where traffic goes to, where it comes from. The controlled indoor environment lends itself to CRAN, and RAN virtualization built on CRAN foundation as a result sees its first applications in buildings and in venues. Scalable, flexible, and future ready for 3GP progression and 5G without having to rip and replace is another requirement which these systems lend themselves to. So now let's get to Dali Wireless, which, by the way, we featured in our Hot Tech Innovators white paper and our Top Technology Disruptors report, both of which are now available on our website. So please don't hesitate to get in touch with us to get a copy. So thank you all for listening, and I now hand back over to Marcus so we can listen to the Dali section of this webinar. Thank you very much.
Okay, thank you, Nick, for the analyst's view on the market trends and market developments. We shall now make a very short poll, a question to the audience. We have two questions. Let's do them one after the other. First question is, when do you think RAN virtualization will be widely deployed in mobile networks? You have three choices: not at all, within the next 2 years, or within the next 5 years. So just for the audience, just please click at the option that you think is the most correct according to your opinion, and we will then show the results of the poll at the end before we go into the Q&A session. I think this will be very interesting. We have dozens of different countries, attendees from different countries here, so we should get a very wide and good feeling of what the audience thinks here. Okay, poll is in progress. Answers are coming in. Don't think too hard, too long, just gut feeling and place your answer. Okay, 10 more seconds. Please place your bets. Okay, thank you. Let's move on to the second question. And that is, here it is. Just think of a large sports stadium and the typical radio capacity that is usually deployed there. Having this in mind, how much of the installed radio capacity do you believe is actually utilized over a period of 1 month? The answers are less than 5%, about 25%, or up to 70%. Do a quick calculation in your head or from your experience and your feeling and pick a number. Okay, we see answers coming in. Don't think too hard about this. This is not analytic. This is just, gut feeling. This will be interesting when we go to the Q&A session, and we will prepare a small chart to show what the audience poll said. Okay, thank you. Let's close the poll as it is and hand over to Wolfgang Weber for the deep dive, the more technical and business-oriented deep dive on RAN virtualization. Wolfgang, go ahead, please.
Yeah, also a very warm welcome from my side, from sunny Vienna in Austria. It's a real honor to introduce such a distinguished audience into the sequence of RF routing, and I want to extend also a special welcome to my former colleagues of Alcatel-Lucent. I've seen many of them in the list of participants, and also a very special welcome to my former colleagues coming from operators around the globe. So it's a very simple task that I have, thanks to Nick that did the heavy lifting. I just will use 5 steps or 5 letters. It's D like Delta, T like Tango, R like Romeo, and V like Victor, and B like Bravo to introduce through to RF router as a basis for RAN virtualization. And let's start with the D, which obviously stands for Dali Wireless. Dali Wireless is a company based in Menlo Park, but with a research and development center in Vancouver. So what we do, Vancouver is for us the virtualized Silicon Valley, if you want, thanks to a great team that's working there, the wizards of RF and digital processing. And this is exactly what we are doing. Dali is specializing on treating radio frequency the digital way. and we call it software configurable radio distribution systems. And that's also the basis for all of our products and solutions. And we are not only covering all the technologies from 2G to 4G, even 5G, whenever it's available. And we also cover, of course, FTT and TDT. So whatever you want, it can be done digitally using Dali's technology. And as such, we also, of course, support all the necessary frequency bands across the globe, including public safety. We are doing this out of the headquarters in Menlo Park, but we also have regional offices in APAC and Europe. And in fact, as you can see, we create a lot of noise in the market. We received a couple of awards recently, all in fact highlighting the importance of RF distribution and in-building coverage or coverage of hot spots, high density areas, which are key, especially when we talk about data services. All this is also covered with a lot of patents, but let's go to what really matters. That's the technology and the solution. So what are we doing with all these wizardry in digital processing of RF signals? So our system, and it's really differentiating, is digital end-to-end. As soon as the RF signal enters our system, it's digitized, and it's then treated like a kind of a very valuable piece of data, and then eventually it's sent to the far end of the system, and then the RF is regenerated. That's the key. You can think of that like kind of a movie camera taking a picture, and in fact a high-speed camera with a high resolution, with a high frame rate taking pictures, and then sending those pictures over distribution network to a movie theater where it's projected on the screen. And this is exactly what we're doing, but not only this kind of taking in, ingesting the picture and sending it, but on the fly we also apply a lot of let's say digital or mathematics in order to improve the picture, to remove blur if we stick to the analogy of movies, or to avoid color ranging, etc. And in fact, this is the basis, the technological basis for all the products and solutions that Dali is using to enable RAN virtualization. On top of this foundation, it's also a very simple architecture. It's just two different types of boxes. It's a two-tier architecture that makes deployment easy and also logistics easy. And it's also fully software configurable, so no truck rolls, no reconfiguration by flicking switches. It's just flicking bits, and the rest is done by software. Another hallmark is the support of multiple topologies, not only star-shaped topologies, but there can be daisy chains, there can be even loops, or a combination of those coming to trees. And that's also an important element, as we will see when we apply this to RF routing and RAN virtualization. And the transport can be as simple as gigabit Ethernet microwave. It can be Cat6, and it can of course be fiber up to 10 gigabits. Of course, the bandwidth that can be carried over that is depending on the capacity of the underlying transport network. Is 10 gigabits delivering an instantaneous band which is of 320 megahertz, which is a lot. So what can we do with that? As I said, we take RF signals and we process them and distribute them. And this is what the RF router is about. It takes input signals, the cells or carriers, as you can see, and these signals generated by those cells or carriers are digitized and then packed into frames. And in fact, these frames also carry addresses. So the frames can be routed to any destination. The destination here in this image are remote radios or remotes. And this is like sending IP packets over an IP network. And that's the reason we call it RF router. The IP packets correspond to frames that carry the information about the RF signal that is fed into the RF router from the different cells. You can think of that like sticking also to the movie analogy. You can think of many cameras generating high speed, high definition, high quality image streams, and these streams are packed into frames of a movie, in fact, the classical movie, and these frames are sent to movie theaters and are projected to the different screens. And it's not just one movie that is distributed to those theaters. There are many movies that can be distributed to many theaters. You see that in the different colors here. Each of these carriers corresponds to the camera, has a specific color, and you can see that also the remote radios or the screens are showing these colors, and that means that you can take many inputs and distribute them to many remotes. That means you can have many movies running at the same time, and they can be distributed to many movie theaters, and the movies can be even switched amongst the theaters, amongst the screen on the fly, and very flexible and even in real time. So this is the principle of RF routing. In fact, taking these blocks, digitized blocks of RF spectrum, and add an address tag to that and route it to any destination. That in fact means that you can create a logical topology on top of the physical topology of this distribution network, and this topology is defined by a routing table that's stored on the RF router, and that can be, of course, manipulated through software. In fact, switching those RF streams in terms of frames from one remote to the other in a very flexible and even in flexible way and even in real time. So what you can see here is you have many inputs that can be routed to many destinations, and that's the hallmark of RF routing. And if you want to apply a litmus test to understand whether a system architecture that's in front of you or an implemented system is RF routing, then it's just three very simple questions. The first question is, does the system support daisy chains of remotes? And does the system accommodate more than one input signal? And the third question is, can different signals or movies, if you want, be routed to the remotes even on one leg of a daisy chain? And this can be configured in a software way. Only if you answer these three questions with yes, then you are in front of an RF router. So these are the key elements that make up an RF router. And you can definitely figure out this was the R of my presentation, and let's now have a look at the products of Dali that support that. As you can see here, we have two product lines. One is the T-Series that consists of an RF router called T-Host and different remotes, high power, low power remotes that can be combined freely in the configuration. And then you have the advanced Dali matrix system that is, of course, modular in terms of the U-bit. That's the, let's say, the RF router is. You can see here consists of many modules accepting those RF signals or the movie streams, if you want, and send it over fiber or other transport means to the remotes. Also high and low power remotes, freely mixable, but they are modular in the sense that you can have more channels, like 4 or 8 channels in the low power and 2 or 4 channels, independent channels in the high power version. So this is in the product side of the RF routing. And of course, this shows all the differentiating factors that are based on this end-to-end digital processing. And the key point is the many-to-many or end-to-end RF distribution that is software configurable. The topology is flexible, the architecture is simple, just 2-tier, and there is an additional nice feature. There is IP pass-through possible also on all connections in the distribution network. So in parallel to the RF signals, you can also route IP traffic to any destination, for example, for Wi-Fi offload. If you want to combine an access point with a remote, then this is the adequate means to do that. Now let's come to the virtualization part. And in fact, virtualization is real. It's not virtual, it's real, and it's real since a long time. In fact, virtualization started back in 1962 at the Dartmouth College in New Hampshire, where one computer G200 was shared in a time-sharing system with many users. This one computer shared with many users, and this was in 1962. Of course, virtualization has shown more momentum in the 90s when the workstation era started to make an impact in the IT architecture, and those workstations supported many processes, and this was the in fact when virtualization allowed to share many processes with many amongst many users. And again, what you see here is this. I think you get it. That's the many-to-many relationship that's also important in virtualization. And virtualization is characterized just by 5 elements. You have a pooled and shared resources that are accessible to users by interfaces. User could be an end user or process. And the system splits the resources amongst those different users that are isolated from each other. And the resources are allocated dynamically amongst those users. And in fact, each user has the impression that he owns an entire system and has all the resources available that are needed. So these are the implementation principles of virtualization. And then the question, why virtualization? Just one simple point. It's economics, nothing else. It's not technical excellence, it's not innovation, it's just economics. Sharing resources leads to higher utilization and lower unit costs. Pooling resources allows for economy of scale, and of course it also impacts positively the fixed variable costs, and in fact dynamic allocation of the resources also allows for reduced variable costs. These are the principles of virtualization. Again, it's a many-to-many approach, and that also applies to run virtualization enabled by RF routing. So just let's take the picture of the workstation with many processes and many users. The many processes in the RAN are just base stations. And these base stations are composed of baseband resources and radio resources. Radio resources also using spectrum. And the RF router wraps around all this and creates a pool of base station resources and allows for routing of those resources to antenna points with remote radios. And this in a very flexible and real-time way. So that's the principle of RF routing applied to run virtualization. And in fact, it shows all the virtues of virtualization. It applies equally to the run virtualization, if it's done right, and if it's a real run virtualization, covering entire base stations. And it's definitely the scalability. That means you can easily assign resources to different coverage areas covered by the remotes. Then the flexibility, combining different standards, different bands, even different makes of base stations and allocate them also flexible across the coverage areas. Then the elasticity of resources, coming back to the poll that you just have answered to, you can assign capacity as needed, not going for the maximum capacity that is rarely used, and that in turn translates into cost efficiency. And finally, most important still, it's the user experience that is very convincing if you have enough capacity at your disposal as a user, because this is also what counts. And now I come to the B part. What counts when we talk about user experience and user paying for mobile services. And these are in fact the benefits of a virtualized RANs. Let's start on the right-hand side, the user taking an outside-in approach. RAN virtualization allows for on-the-fly provisioning of mobile network resources through end users. That's much like cloud-based IT services that are complemented now by telecom services. And an enterprise, for example, can just configure those resources that are needed in a specific situation. For example, resources can be added if an enterprise is hosting a huge conference and with many participants, then most likely you will need more mobile capacity than on a normal working day, and you can do that easily. And of course that on one hand allows the operator to share the resources and allocate the resources only on a as needed basis, and also it in fact translates into lower costs for the end user while maintaining the user experience. So for operators, the benefits are obvious. First of all, you can use all those benefits of economies of scale, better utilization of resources, all the virtues of virtualization if you want, but adding to that, you can easily handle multi-operator situation or multi-technology scenarios, which is these days especially important when we talk about network consolidation. Then of course all the cost efficiency elements apply equally well, and it's easy to handle because it's totally software controlled. And most important still, you can implement the ultimate goal of efficiency and striking the balance with user experience. It means user experience driven network planning. You define the experience that you want to provide to your end user, and that drives in fact the planning for the network, especially for the network capacity, and as such allows you to optimize the cost as a mobile operator. Okay, so far so good. That was the RF routing and virtualization part, but of course there are other technologies out there as well. That's of course small cells. Small cells in fact are not many-to-many, they are one-to-one. It's just one cell, one coverage area, and often it's only one carrier. Maybe newer small cells have two carriers. It's one technology. That means it's not very flexible, it's not scalable at all, and it creates a lot of cost of complexity because you need many small cells if you really want to leave a high capacity in a high density area, and each small cell is a small cell on its own in your network and needs all the data structure, all the configuration work, all the maintenance work, everything in order to provide the user experience. And that means initially, if you have low numbers of small cells, they are a cheap solution, and they are more than adequate in what I call a popcorn rollout. If some hole in the coverage pops up, you just place a small cell and that's it. If capacity is a non-issue, then it's working nicely. But as soon as you try to use small cells to solve a capacity problems, you run into cost of complexity, as I said, and you run also into an interference problem, because adding small cells, of course, adds capacity initially, but with each small cell added, you add also to the interference picture in that. And you reach a saturation when adding additional small cells doesn't add capacity at all because it's just consumed by the interference. Okay, when we go, by the way, the one-to-one relationship also applies to the traditional architecture of macro cells, be it a centralized or decentralized architecture. Now going to CRAN, or let's put it also this way, this is just one movie and one theater, and that's it. If we go to CRAN, there is a kind of virtualization applied, but internal to the base station, so the eNode Bs, and more than one eNode B shares a set of baseband processors. But this might be a many-to-many situation, many base stations sharing many processes. But as soon as we go to the RF and spectrum part, it's again one-to-one. One eNode B, one radio is just one coverage area. So it's many-to-many to one. Also not very efficient. Of course, it provides some economics for the baseband part, which is just about 40%, 45% of the whole cost of RAN. Only a virtualized RAN, Dali style, is providing economies of scale and all the virtues of virtualization to the entire RAN, to an entire group of base stations, baseband as well as radio. And that's the important point, because the capacity of a RAN is limited by two factors. One is the baseband, and the other one is, of course, the spectrum available. The baseband is easier because, in principle, you can buy additional baseband capacity by adding baseband processors. Of course, it costs you money, but you can do it. There is no limitation to that. Whereas on the radio side and the spectrum side, there's a natural limitation by physics. One piece of spectrum can only be used once. And that's the real limiting factor. And only the RAN virtualization, Dali styles, also covers the other 55 or 60% of the cost of a RAN. And talking of costs, there is an important efficiency metric that we are using and applying all the time. That's the megabyte of throughput per dollar TCO. So let's think of an entire RAN and let's accumulate the costs for running and using this network, let's say for 3 years. This is the total cost of ownership of 3 years. And on the other hand, you can calculate the number of megabytes that go through that network in 3 years' time. That's, in fact, the throughput. It's not the speed that counts. And if you now take the number of megabytes and divide it through the TCO, then you get a megabyte per dollar. And that's the important point, because this is also, this kind of throughput is defining the quality of experience for the end user. It's also defining the ARPU, the average revenue per user. And as a proof of this concept, just look at the subscriptions that are offered by many operators. They have a cap in terms of volume of data, and that's exactly reflecting this efficiency matrix. That's the reason it's so important. And now let's compare the different architectures we have been considering here and how they perform when we apply this metric. So look at the linear development, the straight lines. These are different user stories or use cases for traditional and CRAN architecture, and you can see the cost grows linear with the capacity that you add. And the cost growth is even steeper if you have additional bands or standards that you have to add, or even if you are in a multi-operator situation or going from a single to a multi-operator situation. Then the costs per megabyte grow substantially. Not so if you apply RAN virtualization Dali style and virtualizing the entire RAN, the entire group of base stations, then you see that the cost of transporting a megabyte over the network is growing by far under linear. And adding additional bands or additional operators is not as dramatic with an impact on the cost as it is in the traditional architectures. And in fact, this is the impact of virtualization. Again, you can see here, many-to-many allows for virtualization, and that in fact allows for all these benefits that you reap with virtualization. If you look at the left side of the graph, then you can see that, of course, the initial cost might be higher. Coming back to the small cells have a very low cost, but they are limited in their capacity and flexibility. So with adding additional capacity using small cells, you have this linear development of costs. So see with these blue straight lines. Run virtualization starts with a higher initial cost, but if you use it in situations with high density requirements, then you really see the benefits in showing highly underlinear growth of cost with the capacity. So show me the money, and this is what we did is a use case, a calculation of a use case, kind of a business case, and this is a fairly complex, medium-sized airport or a large train station that combines this the airport or the train station with an entertainment center and a business center. This is what Nick has been referring to. Each of these three areas have tidal traffic. They are nicely complementing each other. And if you look at that, just look at the figures here. If you have single operator situation, then the total cost of ownership of this KPI, megabytes per dollar TCO, is 1/3 lower when you apply RF routing and RAM virtualization as compared to CRAM, and even more so when you are in the complex multi-operator situation. Then the savings goes up to 2/3 or 60% in terms of the KPI and the TCO. So that's quite impressive, and it really makes sense to consider that because there is the capacity crunch, and we know that the traffic is exploding, as Nick has been also demonstrating, and the operators have to keep up with this increasing demand, but without exploding costs. And this is what RAN virtualization and routing is enabling. So just to sum it up, a classical RAN just allows a fixed allocation of capacity over the entire network. And that's what I call the one-to-one relationship, one base station, one coverage area, the capacity of one base station just available in that very coverage area. It's one-to-one. CRAN adds a little bit of flexibility. Coming back to this movie relationship, is of course still one movie that in fact is generated by one camera and displayed on one screen in the movie theater, but the image processing that it's done in between uses a pool of shared process. So that's the only advantage of CRAN. It's just making the image processing, or let's say the processing of the protocol stack in terms of RAN, of the standard, more efficient. But it falls short of also being applicable to the most important part of the cost of a RAN, and that's definitely the cost of spectrum, the cost of a RF. Virtualization allows for dynamic allocation, and prerequisite it is many-to-many, of course. Many base stations can be flexibly assigned to many coverage areas, and the RF router is in fact the enabling technology for that. And this is what Dali Wireless is doing, and I hope that next time you go to the movies, you will think about Dali and RF router. Thank you very much.
Okay, thank you, Wolfgang, for an interesting and insightful presentation on RF router. Here we have the results of the poll. The first question, when do you think RAN virtualization will be widely deployed in mobile networks? So interesting, we have 0% who nobody thinks not at all, so everybody believes it will happen. The only question is within next 2 years, within next 5 years, and it's almost 50-50. So that means most likely we will see something like this, RAN virtualization happening wide scale in networks within the next 2, 3, 4 years. Can be faster. We shall see. So thanks for that insight from the audience. The second question is, how much of the radio capacity is actually being used? So we see less than 5% up to 70% are, these answers are almost equal size. Most people think it is about 25%. In fact, when you do the calculations, it is far less than 5%. So everyone who clicked the less than 5% is definitely on the right track, and that is the story of the over-provisioning and the systematic waste of capacity that needs to be done with classical deployments, and that is what RF routing is all about. Okay. Thanks for the poll answers. In the meantime, we have a couple of questions here, and we still have 8 minutes to go, so I think we can take 2 or 3 quick questions. The first one is probably for Nick to answer. It's a market trend thing. Question from the audience: when can we potentially anticipate 5G infrastructure deployment into the US market? Nick, short reply, please.
Okay. Thanks, Marcus. Well, that's a big question, and I wouldn't claim to know the answer. 5G is being discussed and specified as we speak, and what is clear are targets. South Korea Telecom in 2018, I think, for the Winter Olympics, and then Docomo in Japan by 2020. I've not heard of some MNO setting a target for the US, but there's an extreme level of activity from organizations like 4G America. So I'm trying to specify this. So if I was to guess, I'd say sometime after 2020. Thanks.
Okay. Thank you. Thanks, Nick. We have a question that falls in between the two of you. Maybe for Wolfgang to answer. Both of you mentioned that small cells are difficult in scaling up to large venues. Wolfgang, can you give a quick reply? Why do you believe small cells don't scale up very well, please?
Yeah, that's a very simple answer, and in fact I touched the point also in my part of the webinar. There are 2 points. One is complexity and the other one is interference. The technical part is that adding a lot of small cells into a very limited area, of course, creates a lot of interference, and this is jeopardizing the capacity. That means the number of small cells that can coexist and provide capacity in a small area is quite limited. That's one part, that's the technical part. And the other one is more logistics, and in terms of planning, deployment, configuration, maintenance and operation, each small cell is a cell on its own. And if you add, let's say, tens of thousands of small cells, you can imagine what that means in configuring them, let's say reflecting them, or having those configurations and also all other parameters stored in the databases you need in order to configure and run and maintain and optimize a network. So that's the cost of complexity that's in fact definitely higher than using larger chunks like larger cells and distributing them with a fine granularity, distributing the capacity generated by these larger cells in a fine granularity as you can do it with the IF router distribution network.
All right, thank you both. Here we have another one. This is a deep dive technical question. So therefore, I will throw it to Wolfgang. You mentioned these RF packets on the fibers, the movies and so on. So these spectrum snapshots that are transported on the fiber. Does the time frame, does that relate to any specific technology, and if so, to which? So for which technology is the Dali system built, and any preference?
In fact, there is no limitation in terms of timing or granularity, because the most challenging timing is in fact in the MIMO side. And as per definition, and in the 3GPP standards, you need a precision of 65 nanoseconds in order to make MIMO work. And the timing granularity of the Dali system is 30 nanoseconds. So we are well below that, and that means we are very well positioned even to support not only the existing standards up to 4G and including MIMO, but also future 5G standards. So we have a really high speed cameras with a very high frame rate and a very high resolution, and we can even do slow motion that is very smooth, and that applies to these standards as well.
All right, thank you. We have a lot of technical questions. This is a quick one to Wolfgang. What is the supported bandwidth of the system, and how many standards can be routed by the system? So for which bands for which bands is the Dali system designed and built?
As I already pointed out, in fact, we support all bands for mobile communications as well as for public safety, and we could add easily other bands for other use cases or user stories as well. The instantaneous bandwidth on a 10 gig link is, as I referred to, 320 megahertz. And in fact, this is not contiguous spectrum. You can make the 320 megahertz up of 5 megahertz pieces of different parts of the spectrums and also of different frequencies. And of course, what's also important is that if you want to reproduce the signal, that means project it on the screen of the movie theaters, you can have 2, 4, or 8 projectors per movie theaters, and in fact support 2, 4, or 8 screens. That means 2, 4, or 8 parts of the spectrum or standards.
Simultaneously at the same time?
Correct.
Okay. Right. Thank you. Here we have 1 more minute, so a short reply to this one. What about feature parity with the Dali system? Can it exist with LT Advanced, with COMP and FE-IC and these kind of features that we see in the new LTE systems? Very short reply, please, Wolfgang.
Yet yes, it can. It definitely coexists. It's easy to implement COMP even with the Dali IF router. You could even shift capacity from the overlay to the underlay and vice versa. Further enhanced IC, of course, yes, it can coexist, but in fact it's not necessary because the system supports simulcasting that avoids interference up front instead of mitigating later on.
Okay, that was thank you. That was a very quick and deep dive response to that deep dive question. All right, we are at the end of our the hour, and thanks again, Nick and Wolfgang, for a very instructive, informative, and inspiring webinar here. For the participants, if you want to watch it again or selected parts of it, please feel free to go to the Dali Wireless webpage, where you will see the recording of this session. We will send you the direct link to activate this recording, so you can watch again at your leisure. Okay, thanks to the presenters, and thanks for the audience for staying up with us late night, whatever time of the day it may be at your location. Hope to see you again at one of the next webinars, and with that we say thanks and goodbye.